we took, we did a reaction. It's a redox reaction, a reaction that you can do in solution. Now we, in a previous lesson, learned to work out enthalpy change of combustion by doing heating of water in a calorimeter and measuring the temperature change of the water, and then working out from the mass of water that was there, the temperature change of the water, worked out the enthalpy change eventually of combustion of the fuel. We can't do that for this reaction, and that's because it's being done in water, and we're not going to be heating it up with a fire. It's just a very different process, but we can measure the enthalpy change by measuring the temperature change of the water. So if we know, just like before, if we know the mass of the water and we know the specific heat capacity of the water and we know the temperature change, we can work out Q, and then we can then work out delta H from Q over N. And if it's a increase in temperature, it's a negative enthalpy change, so it's minus Q over N again. But there's some things we need to be aware of, some assumptions that we're making, and some solutions to the problems that arise when doing this. Right, this particular reaction is exothermic, and you recorded data on your tables like this one. Actually, can I have someone's data? So for those who are not here, this is the sort of data you'll end up with. So you're measuring temperature of the reaction before, or the solution before the reaction, and in this particular case, it stayed exactly steady at 23.2, and that's just to make sure it really was 23.2, to make sure the copper sulfate solution we were using had got to the temperature of the room from wherever it had been stored previously. We then chucked the zinc into that reaction at this time point here, 120 seconds. We never try to record that temperature there, and then you'll start to see it climb, and eventually it will fall away. So the question is, what temperature change was there? We can get that one, whatever it is. What temperature change was there really in that reaction? So we're going to do this in a couple of parts. We're going to say what we definitely know. So this, remember, is the mass of this is the mass of the water in the pot. So, and we think we know probably roughly what the mass of the water is because we know what volume of solution we used. We used in our reaction 25 centimeters cubed of solution for copper sulfate solution. So we're going to assume here that that's 25 grams of water in that pot. Now the density of the solution, we don't know what that is really, but we're going to assume the density of the water in the solution was 1 gram per centimetre cubed as before, and that is an assumption. It's a reasonable one, but we don't know it for sure. So M is 25 grams, C doesn't change, that's the specific heat capacity of water, but again, this was a solution, so this is an assumption as well. So assume, perfectly reasonable assumption, but it is an assumption and we need to know these sort of details. Assumption that, an assumption that joules per degree C per gram. I had a moment there. Right, and we've got the temperature change, and it's very tempting to just assume the temperature change is the difference between the minimum and maximum temperature. And for that data that I was just looking at, can someone tell me what that data was, the minimum and maximum temperature? 23.2, I think, going to, what was it? To 30.5. Now that would be perfectly reasonable to say the temperature change there was 7.3 degrees C. But I'm going to put that in brackets because that's not right actually. And then we can work out enthalpy change from that, and I'll do that at the end. We've got to work out N of the limiting reactant here, so we need to do some math to determine which is the limiting reactant, to work out the moles of that and the moles of that. We'll do that later on. What I want to spend some time thinking about now is how do we determine the maximum temperature change from that reaction, or the full temperature change. Now the issue you've got is that when you do a reaction like this, it's quite a slow chemical reaction. It doesn't go straight away. So the data you plot will look like something like this. and you've got the gap. There's 120 seconds. So this is time. There's a gap, 120 seconds. 0, 30, 60, 90, 120. We left a gap, and then it climbed, and then it will fall away at the end. And it climbs because it's an exothermic reaction, but it's a slow exothermic reaction. It doesn't happen straight away. So by doing it like this, it allows us to see the reaction proceeding. So it's a slow reaction because it's heterogeneous. In other words, it's a solid reacting with a liquid or a solution. That usually means it's going to be quite slow. So we've got a slow chemical reaction. And this approach allows us to take into account that time taken. But any hot solution will, just like if I brought a cup of tea in here and left it on the side, it will cool down, won't it? And the bigger the difference in temperature between the cup of tea and the surroundings, the faster it's cooling. Some of you might do physics, but might be quite intuitive anyway, but the bigger the difference in temperature, the faster the cooling. In fact, the rate of cooling is proportional to the difference in temperature between the solution and the surroundings. Newton's law of cooling. The point I'm trying to make here is that the reaction is cooling down while it's getting hotter in a way. Cooling down while reaction is taking place. Right, so we do this technique, we've got degrees C, the temperature up here in degrees C, in order to allow us to determine the temperature change that would have occurred had, hypothetically, the reaction been instantaneous with no heat lost. In other words, what the temperature change have been at 120 degrees. So we use this process called extrapolation. So determining temperature change using extrapolation. And the first line we need to extrapolate is this one here. Now, because Mr. Caller's put our copper sulfate out earlier on today, it all got to the room temperature, which wasn't changing, and so that was nice and static. Sometimes if it's been cold, the first point might be down there. We just ignore that. We just extrapolate along that line there. So that's our initial temperature. And that, by the way, we're not going to do uncertainties today too much, but I'm just going to say that might have been something like plus or minus 0.1 degrees C using our thermometers. So how do you work out the maximum temperature change, the theoretical maximum temperature change? This is not obvious, and you'll get this wrong unless you learn it, I'm afraid. So what you need to do is to look at the cooling curve that's going on, which, by the way, at these temperatures, and for this amount of time, looks like a straight line. And so you can use a ruler to extrapolate it back. In reality, particularly for very hot solutions, it will be a curve because of the whole Newton's law of cooling and the rate of cooling being dependent on the difference in temperature of the solution to the surroundings. And notice, it's really important you notice that I've gone through all of those linear points. I did quite well there getting those online. We do not try to bring in this point. This is really common mistakes, just pointing out to you here, folks. Really common in an exam. Just ice this way for a sec, really important point. This point here, tempting to draw your line through that. Certainly tempting to draw through some of these points here. You ignore them. The reaction had not finished until it got to this point. There the reaction finished, and then it's cooling down. So we extrapolate back to this time point here, and then what we do, the temperature change is that's our temperature change, which is considerably bigger than the temperature change if you just look to the maximum temperature on your table. So the maximum the temperature change from there to there might be, say, I don't know, instead of being say 7.3 degrees, it might have been something like 10.5 degrees, and that would give you a very different value for Q and so on. Before you plot your own data, which by the way you will do, I would like you to practice doing extrapolations on this worksheet. So I'm going to do two of them with you. The first one's going to be here. So always using a pencil, of course, and making sure that line's straight, which is not particularly, but you'll do a better job. This one's quite difficult because it really does look a bit like a curve, but we're just going to do a straight line for now. Ideally, it would probably be a curve, and we're just going to extrapolate back to that point there. And clearly the solution, or the solid here, was added at 4 minutes. So that's your temperature change for that one. And by the way, we can do this for endothermic reactions as well. So this is exothermic. And we'll do one for an endothermic reaction, which I'll do with you. Exactly the same process, but it gets colder instead of hotter. So the temperature, the starting temperature is the temperature of the last point. I did my best to draw that straight line. And again, it looks like a bit of a curve, this data, but it'll be near enough if I draw a straight line like that. So both points, ignoring that point there. And then working out the temperature change at the point where where the solid was added. So we've got a temperature change there. You can work out then those numbers using your data. Sorry, using your lines. Work out that temperature change and that temperature change, please. And do the same for the other two. And what we'll do in the end is do that for your actual data that you measured in this class. So hopefully you've got an idea of how to do those. You'll do it for your own data, and I'll have that in at some point when you've had a chance to do it. But we also need to work out delta H from this. So delta H of this reaction is equal to minus Q that we work out from our temperature change divided by N. But you'll see on the worksheets that the limiting reaction, the limiting reactant of your reaction has already been worked out for you, which is the number of moles of zinc that you have in the reaction there. And you're told, so in other words, all of the zinc would have been used up in the end, and you had a mass of zinc that was 0.5 grams. And the formula mass of zinc, the atomic mass of zinc is 65.39. So we can work out the number of moles of zinc, and then that's what we do to work out the enthalpy change. So if you could just do that for me, Olivia.
0.0076.
So there we go. So that's all we've got to do. So what I'd like you to do between now, well, before we're done for the year, I'd like you certainly to have got your data plotted onto a graph looking exactly like this, but on a graph paper. A value for Q determined by doing M times C times delta T, and then work out your number of moles of zinc and work out enthalpy change, please. Hopefully that's very doable, and that's where we'll leave it. I'll give you some graph paper.